Okay. So for the next hour or so, hour and change, I'd like to basically do a live demo of some profiling tools and also talk to you about the homework assignment. I'm going to kind of bounce around a little bit. So if I go too fast through something or if you didn't catch something that I said, please holler at me. I get a little distracted sometimes. So just let me know. The homework has been posted. You can see it here. Whoops, I didn't code up that link properly. Well, I'll fix it there. If you if you want to use the Linux machines here on campus, which is what I use to test all of the homework assignments, everything is guaranteed to work on these machines. You actually need to go to a website. So if you click on this link here, don't click on this up here. That's my mistake because I am horrible at web programming. It's not even web programming. Click on this part where it says click here, and that'll take you to a website eventually. The EQ website. This is a brand new system. You guys are actually the first students that are getting your hands on this. The faculty has been doing a test of this system for the last semester or so. This is the first class I think that's actually getting to use this new software. So the way that it works is instead of having the Linux lab that they used to have upstairs where I used to teach this class, all those computers are gone now. I don't even know what's in that space anymore. It doesn't really matter. And instead, they've just got like a few server racks set up with Linux installed on them, and then you connect remotely to those servers using this tool. And so you can use this to do all of your homework assignments, and you should be able to access this off campus as well. So if you don't want to take the time to set up a Linux virtual machine on your box, then you can use this system instead. The way that it works is you go up to submit job. This website I found is a little slow at times, but once you get the machines up and running, they're normal speed. Is this doing anything at all? Come on now. Okay, got it. Yeah, we're all slamming it at once, probably. And then we want to start up a Linux desktop. So once I click on Linux desktop, at some point it's going to ask me to log in, I think. I don't know if that's now or later. I don't remember. Or never. All right, cool. So I have the options that I can set here. Maximum runtime. It's set to a day by default. I would actually try to be, you know, a little bit cautious about this. I would say error on making it smaller, because if you type in, you know, like 10 days or whatever on this thing, then you have that box reserved for 10 days, and nobody's going to be able to use that box for that 10 days, which might sound awesome for you, but if we run resources, then you're going to get an email from me being like, hey, man, what the hell? You reserved a box for 10 days. Are you actually using it for that whole time? Right? So just reserve it for a time that you know that you're going to need it. Or an alternative to this is you can release it once you're done. And since this isn't working, I'm going to go that route. Oh, I see. I have to click the little clock. My apologies. So I'm only going to need this for a couple hours at the most, right? You can set your screen size, whatever. If you want to upload files to it, you can. It does have access to the internet, so you can just download files from wherever you want to as well, which I think is what I'm going to do in this case. And then click Submit Job, and it will give you a thing to download. I think it's a JNLP file, which I actually don't even know what that stands for. Java something or other, I believe. And once that gets started, once that job, here it comes. It's creating the job for me now. Once I get that file, did you guys steal all the resources? Am I going to get locked out? Is that what happened? It was much faster when I did this earlier today. Here we go. Got it. Right. I download this JNLP file. I've got like 100 of these things on my laptop now. So many of these files. And open it up. And it gives me a remote connection to a Linux box. Yes, I want to do that. Here's where it asks me for my login. This is your Woozle key, just like normal. And then bam, I've got a remote connection to my Linux desktop. I actually don't know what flavor of Linux this is, to be perfectly honest with you. I tried to figure it out earlier today, and I got distracted, as I tend to do. I never actually figured it out. It's not particularly important, I suppose. Oh, hey, where'd that come from? Oh, yeah, I guess I put that on there earlier. Anyhow, box to use. And for the purposes of today's demo, I'm going to come on and grab a copy of that memory mountain code and put it on here. I'll just use wget. Actually, let's see if I can make this text a little bigger while I'm in here. Control plus. Okay. Good to know. All right. I'll just use wget because I know the address. If you don't know the address, there is a browser. See this generic browser down here. Called mountain.zip. There, it pulled it down, and then I can just unzip. I'm just grabbing this so I have something to use to show you for the demo. Actually, I can show you how this works. Wish this was bash. Let me make this bash. That's better. All right. So here's the memory mountain code. We can take a little detour and show you this one real quick. Whoops. Awesome. Oh, that's just a warning. Who cares? Not my problem. So it did work, correct? Or not correct? No, it did. There's where's my syntax highlighting? That's what I want to know. Where's my file highlighting? I miss it. Anyhow, this is the memory mountain code that I used to generate the plots that were on the slides. And so if you look here on the top is the stride, and across the rows, which unfortunately by making the text too large, I screwed up the display. But down the columns, or down the column, you see the working set size. So how big are the actual arrays themselves? And then these are the actual memory throughput values that are computed. This code is a little out of date. I think it should be extended to increase the working set size and the stride size, actually, because modern day caches are better, of course, than when this code was originally written. But how fast did this code actually run, right? If I want to measure the performance of this code, how can I do that? That's what I want to talk to you about for the rest of the day today. So we need some tools to help us. Let me go back to my slides here now that we have this set up. This is the area of profiling. So we need to profile our code. If we want to optimize program performance, we have to know what the performance is, right? We have to know where we are in order to have some kind of improvement. We have to be able to measure performance. So we're going to use profilers for this. Actually, I'm going to talk to you today about gprof, operf, or also called oprofile. And then I'm actually not going to talk to you about gperf tools today because gperf tools is not on the Linux box. It was on the old Linux lab, but it's not in here. I've swapped gperf tools out for a separate profile called perf that I'll talk to you about instead. If you want to use gperf tools, if you have Linux on your machine or you have a virtual machine or something like that, and you want to download gperf tools and use that, you're more than welcome to do so. Or if there's another profile that's not on this list that you want to download and use, you're more than welcome to do so. I'm just going to talk about these three for today. So let's get started with that. gprof is the first one I want to discuss with you. It has been around. Linux box, any Unix box in the world has gprof on it. It's part of the GNU library, right? So it's on there. In order to use it, you have to compile with a special flag. You have to compile with this PG flag. So if I go back into my Linux box here, I don't think this makefile has it in there, but I can update the makefile real quick to make sure that it has it in there. what did I say? PG was the flag. So put those in there, and then I'll need to remake it. All right. So now it should have made it with the PG flag. There it is, right? Don't ask me what PG stands for. I don't know. Now we can use gprof to profile this code for us. Okay. The way that we do that is we execute the code as normal, right? So I'll just go ahead and run this again, mountain. It does take a bit of time. And now if we look, did it work? Oh yeah, it did. Now if you look, there's a new file. Because I included that PG flag, right? There's a new file after this code executes called gmon.out. And that contains the results of the profile. That contains the results of the performance results of that execution. So to examine those results, I can say gprof gmon. Oh wait, I need to say gprof mountain. Actually need to say the name of the executable. And then scroll up to the top here. And so up here at the very top, we see a list. This is going to be the flat profile. So it's a list of timings. Over here, this is the name of a particular function within the code in C. And then this is the total amount of time in seconds that it spent in that particular function. So you can see in this inside of this test function, it spent 0.16 seconds. Inside of the run function, it spent a hundredth of a second. And that was basically it. The remaining says 0. It wasn't really 0, right? It was just too fast to actually get a sample of it. If we take a look at the code, we can look at the mountain code and see if that makes sense. VI, hello. Oh, wrong keyboard. Keep doing that. If we look at mountain.c, right, there's main. Main looks like it's just printing a bunch of stuff. Yeah, main looks like it's just printing a bunch of stuff. Init data, that's what's going to create our matrix. You see it just sets it all to 1 because we don't really care what's in the array. The data is irrelevant. And now test. Oh, hey, this is the actual one that's doing all the work. This is the one that was on the slide earlier, right? This is the function that was on that slide. So here we see the stride length. Where's my syntax highlighting here too? Oh, this is going to drive me crazy. Right? So this is where the brunt of the work was going. That makes sense. That meshes with the results that we saw from gprof. Most of the time was spent in that function, right? Cool. And so then down here, what we see is actually a second piece of information that gprof gives to us, which is a call graph. So this shows us not just execution time, but also if I call another routine, right, if I call another function from within a function, it includes that aspect of things as well. So I can see not just how long I spent in the actual function, but within one of the children, within the child calls of that as well, and how many times I actually called each of those. So you see here, I called test 7,872 times, right? The way that it works is the one that's sticking out. See how these are sticking out? The primary ones, right? Anything that's above is what called this function. Anything that's below was called from this function, right? So that's why it's called a call graph, because we can see the relationship of all the function calls. So this is who called me, and then these are all called from this particular function. And then we can see how much time was spent in each of those child calls. If you look, you can see that 0.16 seconds was spent in test, which is a child call of this oddly named function. But then in the second column, we see the amount of time that was spent in each of the children, right? So this time gets added to the time of the child for this function. And so we can see how much of that time was actually spent inside of the function itself and how much time was actually spent in child calls from that particular function. It's to give us a further breakdown of the data. Recursion makes these call graphs look a little tricky. Hopefully, I don't think we're going to run into that problem in this particular class, but if you do have recursive functions, these call graphs get a little tricky. So just keep that in mind. And then it does spit out a whole bunch of information about what this stuff actually means. For the most part, though, I mean, you can see that for us, it looks time is mostly what matters here. How much time did it actually spend? This is in seconds, I believe, right? Yeah. So it just gives us one particularly useful value. How long did this take? Which is a good measure for performance, I think. Let me switch back to my slides and that I needed to cover. I don't think so. I don't think that I did. So we covered the flat profile. We covered the call graph. Error. Let's talk about error analysis with gprof. It's not a perfect tool. There are no perfect tools. All tools have their problems, right? gprof, being old, perhaps has some more issues than others. So what are some potential sources of error with this tool? Can anybody think of any? Overhead. How do I get those samples, right? How does that actually work? Does anybody know? Has anybody used gprof before or no? So the way that it actually does that is it has to periodically stop the program and say, hey, where are you right now? Right? But in order to do that, the program is going to halt. So the time is going to be inflated a little bit. They try, of course, to keep that as lightweight as possible, but it's not zero time, right? It's some time that took place. There's also this issue of, you know, if I look at the results here, there are some functions that, oops, there are some functions that look like they didn't execute at all because the time is 0. Why did that happen again? Yeah, so the time between samples, right, was longer than we actually spent with inside the function, right? So in between polling, that function executed, and I missed it. Yeah.
So this sample doesn't actually know which
it can use static analysis to determine how many times a function was called. Yeah, and that's what you see here, right? Number of times functions were called, right? That's what these are. Yeah, called. And so you can see it can tell how many times something was called, but if it doesn't, it's also sampling. It's also stopping at periodic times. And if it doesn't hit in that function at one of those times, then it looks like it spent no time in that function. Even though we know that we executed this one 3,000, almost 4,000 times, right? Yeah, so that's kind of the drawbacks. Those are the major downsides. If you look online, if you look at the gprof documentation, for example, they do a little bit more in-depth treatment on the error associated with gprof. You know, one solution you might consider is, hey, I could just increase the number of samples that I take, right? And then eventually I'm bound to start getting samples that will appear in these functions, right? Well, that's true, but the more samples you take, the more overhead you're imposing on that program. The more extra time you're inserting into that program. So it's a trade-off. By default, I think the sample size is, actually, it should tell me. Each sample hit covers 2 bytes for 5.87% of 17 seconds. It should tell me the sample size. Each sample counts as 0.01 seconds. So this would have only taken then 17 samples, right? It's taking 100 samples per second, which is actually kind of large if you think about it. That's a pretty large sample size when we're talking about computers. Yeah, so that's gprof. The nice thing about gprof is it's dead simple to use. It's so easy to use, and it's been around forever. And everybody knows about it. Everybody knows how to use it. Okay, but it does have its problems. So let's talk about some additional profilers that we can use to maybe help with some of these problems. I want to talk about operf next. Operf is the name of the command, but the library is actually called oprofile. I always call it operf because that's what you actually type into the terminal to make it work. OPERF works a little bit differently. It maintains counters for various events. And these events are both hardware-based and software-based, right? And so then we can use these events to help us track the performance of our program. If you want to know what the events look like, let's take a look at what those events actually look like. What do I mean by events? I can type op help. I'm going to use that wrong keyboard again. All right. And it will list out all of the events that are available. You can see it's kind of a long list, right? Oh, man. It's still going. So there's a lot of stuff in here. Whew. Still going, still going. Goodness gracious. Yeah. My finger's going to fall off if I keep scrolling like that. All right. So it's quite a large list. I'll be perfectly honest with you. I have no idea what all of these counters are. There's no possible way that any person would know what all of these counters mean. Let me see if I can shrink this a little bit. But there are here that I do understand that I use on a regular basis. Let's see if I can find them in this giant list. There's a lot of stuff in here with caching that we saw. So here we see L2 miss. How many times did I miss the L2 cache? Right. There's also L2 hits. How many times did I hit the L2 cache? So if you want to investigate memory performance as it relates to program performance, those could be some useful counters, right? Cache performance. There should also be some up here for, oh goodness. It's such a long list. I know there's one for like clock cycles, for example. I know there are some for, yeah, so here we see these have to do with clock cycles, it looks like. Here's a whole bunch more that I don't know what they do. Switches, penalty cycles. I know there's some that count context switching. Are you guys familiar with context switching? What does that relate to? Saving the state of the processor so I can do what? So that I can swap out the thread for something else, right? I'm basically time sharing my processor. So there's not just one program executing, there's lots of programs executing, and I have to go through and give them all their fair share. In order to do that, I have to do context switching. But that takes time, right? So the number of context switches is going to have an effect on performance. Here's a whole bunch on conditionals, how many branches were taken, et cetera, et cetera, et cetera. So I'm not going to go through all of these, of course. That would be silly. But you should take a look at this list and pick out ones that you think would make sense in terms of performance. And you can check the documentation online as well. I did link to the documentation on the course website. So you can take a look at that too. So if I want to track events, right, there's a couple different ways I can use OPERF. If I want to track events, specific events, then I have to pass in a particular flag. So it'll be OPERF-E, and then I can list events after that. So let me find an event to try here. What was that called? Where was one of the cache ones? Here we go. L1 miss. Let's try that. L1 underscore miss. Oops, that's not a 1. Miss. And then you execute your program on the end of this. And it didn't work. Awesome. Help me out here. OPERF options. Did I not spell it out case sensitive? I thought it was all lowercase. Well, you can also do it without any events, and I believe it'll use clock cycles by default. So if I say OPERF, just mountain, profiler started, runs the code, profiling done, right? So it actually did it. Right, but where are the results? In order to examine the results, we have to use OP report. So if I look at the results here, it should have give me another file, O-profile data. If I want to examine the results, I have to use OP report to examine that. And now, inside of OP report, you take a look. It did use clock cycles by default. This is the default event that it uses, unhalted clock cycles. And so you can see that during the execution of this code, I had 3,942 clock cycles. What are these down here? Anybody know? It could be from other processes. It's also like system, libc, that's the library, right? We're using C library stuff, system calls, right? To print out information, stuff like that. So it's really, and notice that it didn't give me the functions themselves. It just gave me the number of clock cycles for the entire chunk of code, for all of it, right? So if I want more detailed information, if I want a call graph included with this, I have to run the profiler a little bit differently. I have to say, I have to use the dash G flag. So operf dash G and then do it. I'll let it run again. And now this time I should, if I run OP report, I should get a call graph, except I didn't. Awesome. Way to make a fool out of me, operf. Oh, to display a call graph, then I have to use -cl. There it is. Here's my call graph. And you'll notice it's in a very gperf-like format, except for you can see that just like we saw in the original, it's including library calls and things like that in here as well, which gprof did not do for me. So a lot of these down here may or may not be relevant to what we actually are trying to measure. Here's main, right? So the number of, remember these are counters, so total number of samples that I took, right? And then the percentage of overall samples that belong to this particular item. So out of all of these, tests had 88% of the total samples that were taken. Which again are clock cycles in this case. Now you need to be a little bit careful. You might try to get clever with it and say, I know how many clock cycles it was, right? And I know what the clock speed is. In fact, it even tells me at the top what the clock speed is when I execute the code. So if I just multiply the two, right, then I have an estimate for time, which is true. You do have an estimate for time, but it may not actually be accurate. Why not? What's the problem with taking the clock cycles and multiplying by the frequency and using that as an estimate for time? Yeah. So multi-core could come into play if you've got multiple cores, right? That's going to inflate your clock cycles quite significantly. There's other issues as well. Does my CPU always run at that speed? A lot of times today, the answer is no. Your CPU will ramp itself up when it needs to and slow itself down when it doesn't have as much stuff to do. And there are outside factors that can make it do that, right? It's outside of your control. You can't tell it to speed up or slow down. It just does it. Just does it based on the firmware, right, of your CPU. So it'll get you in the right ballpark. I'm not saying it's a ridiculous number and you should never use it. It'll get you in the right ballpark. But using that value as an actual representation of time, I think is a little problematic. If you're going to use it as a representation of time, just use the clock cycles value directly. Don't try to convert it into seconds. I think that's asking for trouble. Just use the number of clock cycles. If I remember properly, I don't think there actually is an event here for actual seconds, like wall clock time. I don't think that's something that O-profile does. Remember, it's hardware and software counters. Your computer isn't sitting there. Your computer's not worried about the time on your watch or the time on the clock, right? Hardware and software deals entirely in clock cycles. So that's what it's concerned with. Let's see. I have in my notes here another option to try this with, but I actually don't remember what that option does. So let's just try it and see. In my notes, I have dash symbols. Let's see what that does. Oh, perfect. So it gives me a scaled down version of what we just looked at. Dash symbols declutters that call graph a bit. Less information, but also a little easier to read. And so you can start picking out, right? Everything labeled mountain comes from the memory mountain code. Here's libc code, malloc, free. Cool. Let's see what else I have here to show you. Oh yeah, this is fun as well. I'm actually a big hardware guy. I love talking about hardware. There's another neat thing you can do with OProfile called Open Annotate that allows you to actually examine the assembly code for a given program and see how many times individual instructions were run. So that can be very useful if you want to take a look and see if there's a computation bottleneck somewhere, right? One particular computation is hogging a huge chunk of the running time of your code, for example. So let's see if I can get this to work. Open Annotate is the tool. So, oops. Open Annotate source. Let's see if this works. Oh, it's not on here? OP, thank you. My fault. So I may not have compiled it properly. You do have to, let's see. There might be a compiler flag that I'm forgetting here. Lost samples detected. Well, that's not good. No debug information. Oh, I probably need to give it a binary. That would help. Nope. Well, shoot. What did I do wrong? Source. Ah, there we go. I had to pass the assembly flag in as well. So now you can see all of the assembly instructions, and it should list, gosh, that's a lot of instructions. It should list profiling information for these as well, but it doesn't look like it actually is. Step jumps. No, this is just the actual assembly itself, which is interesting, but not really what I wanted to show you. It's telling me lost samples detected. I'm wondering if there was a way I was supposed to compile this to make it work that I forgot. Or lost samples detected. Huh. Or another thing that can get in the way is optimization. Are you guys familiar with optimization flags with the compiler? O2 is a pretty high level of optimization, which makes it tricky to determine where I'm at within my program because it starts doing things like function inlining, where it removes all function calls and just copies the actual function into each of the places. So if you ever run into trouble profiling, you might try taking the optimization flags off, which is what I'm going to try and do now, and see if I can get better results. It'll run slower, of course, but if you can get more information, then it might be worth it. Let's see. I need to say OProfile. Or no, I need to say OPerf. Oh, come on. Oh, I do. Thank you. That would help, wouldn't it? I don't know if that took longer or not. Let's see if we get better results from our assembly here. I still don't see any profiling information. That's frustrating. Why didn't I get that to work? It should taken at each instruction, and that number is a percentage of total samples, but it's not cooperating with me. It's just dumping out the assembly code by itself. I need to compile with the G flag. That's what I was suspicious of. -G. Thank you. It's in the documentation, which I'm being stubborn and not reading right now. Like a true programmer. All right, and now I should hopefully be able to say, so that actually works. Now I can see it as a function of source. So this is not assembly, obviously. This is just the source code itself. Where are my samples? Yeah, I think it's these random values in here. So this is 4, right? Total samples for file. Ugh. So much. I hate scrolling with this trackpad. It's frustrating. Yeah, so up at the top, oh shoot, I just saw it. Up at the top, you can see the total number of samples as a percentage, right? And then interspersed throughout the file, you'll see other values and the number of samples, right? So here in this loop, we see I took 123 samples. I took about 1% of my samples just within inside of this loop that initializes the code. Here, okay, we see we did a lot of work, right? Inside of this loop, I took a ton of samples. This is that test function again. That's what I expected, right? So it gives me a line-by-line source code of my source code and how many samples were taken in each particular, not each particular line, but within the lines that did a lot of work, right? Why don't I see samples here? I'm just gonna run too fast. That's a very small amount of instructions, right? I'm not spending a lot of time there, so the chances of me hitting that with a sample are slim to none. You see the samples are gathering where I do most of my work. So that can be a useful tool as well. Some random samples down here. Cool. Let's see if I had anything else to show you. Nope, I don't think I had anything else to show you about that particular tool. So let's move on to our third and final tool. And then we'll talk about this homework assignment a little bit. Talked about OP report, talked about OP annotate. Oh, this is the old slide deck. That's not good. My apologies. I forgot to copy the new slide deck up. Well, I might leave this one up just in case you decide to use gperf tools. If you want to use gperf tools, I might leave this one up just so you can see how to do it. Let me pull up the appropriate slide deck real quick, which is going to be this one. Should be right around. That's also not right. Where are my slides? Oh, it's this one. Perfect. Here we go. I got it. Perf. Yes. So perf is actually an iteration on OProfile, the one that we just took a look at. Some people had a problem with OProfile. They didn't like some things about it, so they decided to improve it and make it better. So again, it's event-based. It's relatively new, but it's starting to gain a lot of traction within the community. It has a Git-like interface. It tells you, honestly, it tells you a lot of the same stuff that OProfile does, but in a better fashion, perhaps more intuitive fashion. Oh, that last line is no longer relevant. Man, I changed all these slides and it didn't save. Sorry about that. I'll fix that after class. It is also based on events. And so let's take a look at the list of events that perf has. For perf, it's perf list. That's how we get the events. And these are a little easier to read, you can see, than the last one, right? List of predefined events, CPU cycles, instructions, cache references, cache misses, CPU clock, task clock, et cetera, et cetera. It'll use CPU cycles by default. This is not the entire list. I'm just not scrolling down yet. So there's L1 cache stuff, right? Number of branches. These events, for the most part, also exist in OProfile as well. It was just a little harder to read that list that OProfile gave us, right? And so to use perf, it's very similar to OProfile in that you can specify which events you want with the -e option, which did not work for me last time. But let's try it again with this one. If I want to say perf -e, which event do I want to use? Let's pick an event. Let's say, so LLC is lower level cache, which on this machine, I can't remember if I have 2 or 3 levels of cache. I think I might just have 2. Let's try L1 Dcache. L1 D cache load misses. I'm probably going to spell it wrong, but. And then run the code. Oh, great. Unknown option E. Always, 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 always. I do a great job of. Why isn't that E option working for me today? That's frustrating. Here. Oh, perf stat. I forgot to. Yeah, I was getting ahead of myself. Sorry. Let's take a look at this one. Perf stat is how we actually grab the counters. There's my -E flag right there that we're going to try in just a second. So this is what we'll actually use to tell it to go out and start the event counters. And so here you can see one, right? This is what I was trying to do. I just forgot the perf stat. We can try that in a second. It's going to include kernel information as well. So things that the operating system is doing. You probably don't want that data. If you want to exclude the cache misses from the operating system, for example, you need to use :U on the end of the event to exclude anything from the kernel. I'll show you that example in just a second. The nice thing about perf, one of the things I love about perf stat is if I pass -R and then give it a value, it'll run that program 5 times, for example, and I give it 5, and then spit out the mean and standard deviation of the results. Which is very useful. So hint, hint. You might want to take a look at that for the homework assignment. Let's try a few examples with perf now that I took the time to read the instructions as I should have before. So what I really wanted to do was something like this. But I just need to put perf stat out front. And it still isn't working. Awesome. Oh, capital L, thank you. Awesome. Got it now. Here goes the code, and you see how many cache load misses that I have, 32 million. Woo, that's a lot. This one does tell me how much time elapsed, 2.5 seconds. Right, that's nice. Profile didn't give me that. Some of those cache misses are going to be due to the kernel, due to the operating system. So let's stick a :U on the end and see how that changes. Even more. Exactly what you thought was going to happen, right? But you can see, I mean, this number is variable. It's not going to be the same number twice in a row. Actually, that was very close to the same number twice in a row. It's going to vary a bit. There are other factors in play here, right? The operating system's constantly switching this out. Other programs are using the cache, which is making this not entirely accurate, which is why it's important to take samples. So you can do something like -R 5 and then run it, and it'll run it 5 times in a row. This is going to take a little longer because it's going to do it 5 times. It should take about 10 to 12 seconds. Cool. And so now I see that the average number of cache misses was 32 million, plus or minus 0.61%. So that's the variation, an indication of variation. And the execution time was averaged at 2.53 seconds, plus or minus 0.18%. Right? The one downside with this is I can't really see each individual sample from this output. I can only see the aggregates. So if you want to do any additional processing, that makes this tool hard to use. But I'll let you determine the best usage of that piece of information. If you don't include any events, I believe it does use clock by default. If I take this out, you use clock cycles by default. Oh, actually, it gave me a whole bunch of stuff. Awesome. So here's clock cycles. Here's the number of context switches, number of page faults, which is also due to caching clocks. Oh, task clock. So that's actually in milliseconds? No, that's in seconds. Have to be, right? No, that's in milliseconds. My apologies. I can't math today. Cycles, instructions, 1 billion instructions. Branches, branch misses. Branch misses, do you know what those are about? Why is it counting branch misses? Where do branch misses come from? How do I miss a branch? It's using branch prediction. It's using speculative execution So if I come along if I come to an if statement, right, I'm either going to go left or I'm going to go right. And it's going to try and examine a number of various factors to determine and try and predict which direction I'm going to go. If I'm in a loop, for example, right, I'm probably going to predict that I'm going to go back up to the top of the loop, because that's going to be true for every single one except for the last one, right? And so branch prediction will fail for that very last iteration. But it's considered a small price to pay, because if branch prediction is correct, then I don't have to stall my pipeline and wait for me to determine which branch I'm going to take. Otherwise, I have to stall out the pipeline.
Branch prediction, is that all determined before you run the program? Like where is that?
No, it's determined at execution time. Yeah, there's feedback from various phases of the pipeline to previous phases of the pipeline. So I can take a look at stuff that's coming out and then feed that back into the pipeline to determine whether I'm going to take a branch or not. And without branch prediction, I have to sit there and stall and actually compute the condition. Wait. And then as soon as I know which branch I take, then I can start feeding instructions through again. Yeah. Even if you only have to be better. You only have to be predicted correctly half the time or more in order for it to pay off, right? I guess it depends on how big your pipeline is. But yeah, sorry, that's more computer architecture stuff. But I love that kind of stuff, and it's important. It definitely matters. Let's see what else perf can do for us. That's not all. There are other things. Whoops. Wrong slides. I keep going to the wrong slide deck. So we talked about that. Perf record. Is used. So perf record will filter out everything. I believe that's the problem that I had with perf stat, is that even when I did this, so even when I filtered out the kernel level stuff, there are still other programs running that weren't kernel related as well, potentially, right? And so that's why my numbers were still about the same. Perf record will focus entirely within a single program. And it's run in very much the same way. Let's take a look at how that works. Get out of here. Wrong keyboard again. All right. Perf record. And then I think I just do like this. It's going to spit out an output file again. Perf.data is what it's called. It tells you how many samples it took. In this case, it took 4,300, almost 4,400 samples. And then to examine it, I have to use perf report. And now I can see that everything is within mountain, right? Here's my kernel calls again still, though. They're still included. But now I can see the number of samples. And the event by default is going to be clock cycles, right? So 97% of my clock cycles are spent within this test method. So you can use that as well. It's just a slightly different take on perf stats. It also lets you store the data. So if you want to process it later, perf stat doesn't. It just spits it out to the console and then you're done. You have to pipe it out into a file or something if you want to keep it. I keep going to the wrong slide deck. All right. We're almost done. We're almost ready to start taking a look at the actual homework assignment. Oh yeah, this is a good note though. If you want to change the sample rate, you can use the -F flag. So keep that in mind. Yeah, so we did perf report. And then perf annotate does very much the same thing that oprofile annotate does. So I'm not even going to bother showing it to you. You do have to use the compile flag, which I remembered to put on the slides this time, GDDB, when you compile if you want to make it work. Cool. All right. Yes.
I don't know which one was, but you said on the screen.
The default here is 1,000 samples per second. The one, gprof, I think was the first one. It was only taking 100. Yeah. Gprof, I believe you can change the sample size as well. I just don't remember how to do it. And again, you have to remember gprof is ancient, so yeah, it does show its age. compared to these other tools. Perf has the most bells and whistles of the three. We kind of went from the bare bones, work our way up to O-Profile, which was better, and then Perf, which is kind of the most feature-rich profiler of the three that we've taken a look at so far today. Cool. Any other questions about the profilers before we talk about the homework assignment for a little bit? Great. So what we're going to do for the homework assignment, let me pull it up on the website here real quick. What we're going to do for our homework assignment is, actually, I want to leave that window open. So I still have something I want to show you there too. Cool. So you see the due date down here as well, June 23rd, Tuesday. We have class on that day. That's a week from Tuesday. It should be plenty of time. This first homework assignment is kind of simple and straightforward for you. At least I hope it is. Just to sort of get you used to what I expect from the homework assignments. It'll be due at 5:30, so at the very beginning of class, basically. I'll talk about all that in a little bit. So for this homework assignment, I've given you a piece of code, homework1.zip. And then down here, I've asked you, I have 9 questions here. You do not have to answer all 9 questions, right? I want everybody to run this answer this first question. So we just went over those 3 profilers, gprof, O-Profile, and perf. I want you to compare and contrast the 3, both in terms of accuracy, overhead. Which one do you like the best from a user interface standpoint? You can talk about all that stuff too, right? I expect you to take some samples, right? Run the code, which is a vector matrix multiplication operation. We'll take a look at that in just a little bit. Run the code with each of these profilers, right? Take a look at the results and tell me what you find. Write a few paragraphs about it, right? Tell me what you figure out. Do some research online. Take a look at the documentation. Tell me what you figure out. So I want everybody to answer this question. Every single report should do this one. And then once you've got that one done, and I also recommend doing this one first as well. Once you do that one done, I've got 8 more questions down here. You get to pick any 4. Any 4 you want to do. I don't care which 4 you pick. Pick the ones that are interesting to you and run them. We can do a quick overview. So end-to-end timing. So timing hooks. What I mean by that is, what if we do manual timing? How do our manual timings compare to the profilers? If I just go in and I use, I think it's get time of day is the C library function to that you can use to measure time. What if I just go in and I manually time the code myself? How does that compare with the profilers? What can we learn about cache organization? So that's the memory mountain. That's what we just talked about, right? What can we learn about compiler optimizations? So change the compiler optimization levels. There are at least 4 or 5 different optimization levels that you can vary. Change the compiler optimization levels. Take a few samples at each level and tell me how it affects performance. Look at the documentation for the optimization levels and tell me why it affects performance in that way, especially as it relates to this specific code set. Pre versus post multiplication would be vector times matrix versus matrix times vector. What's the performance dependence on the size of the matrix? That's actually pretty easy to change. I'll show you that in the code in just a little bit. If I have multiple copies concurrently executing, what if I use a linear algebra library instead of writing the code out myself? I suggested BLAS here as an example of a linear algebra library that you could use to pull this off. I'll leave it up to you to read the documentation onto how you get that library set up and how you actually use it. You don't have to use BLAS if you want to use something else. This would actually be a good problem if you wanted to do stuff in a different programming language. This would be a good one to play around with, because you could use all kinds of different languages here if you wanted to. And how do any of these change if I run them across different machines, right? So here I'm allowing you to compare this to the Linux machine that I'm using versus your own machine or somebody else's machine, right? In addition to that, in addition to these 8, if you think of something else that you're really, really interested in, that you want to start digging down, I'll open that up as well. You can replace one of your 4 with a prompt of your choosing. The only thing that I ask is that you clear it with me first. Just shoot me an email or post it on Piazza, right? Oh, hey, I thought it'd be really cool if I did this. Is that all right? And the answer will almost always be yes. I just want to know about it so it doesn't catch me off guard when I start grading your assignment. And so there's some additional instructions down here. In order to analyze the results, this is very, very important. I need to know the specifications of your computer because it's going to be very different. If you use the lab machine, if you use one of these, then you can just say, oh, I used one of the school machines. I know the specs of this computer. Or if you want to get some of the specs of this computer, you can look in proc CPU info. Will give you information about the CPU, including the number of cores. I've got 8 cores on this guy, right? It will also tell me the cache size, although it didn't break it out for me. I thought it would break it out into L1, L2, but it didn't do that for me, unfortunately. So this will give you some information about your computer, but this isn't all the information either. Your memory is also important, right? How much RAM I've got. So you're gonna have to do a little bit of digging to get that info back out. But please let me know. If you're running on a virtual machine, that's gonna also have some implications, so I wanna know that too, right? Make sure to include that in your report because that will have an effect on your results. And you might wanna talk about how that affects your results a little bit. Tell me how you collected the data. I ran the program using these options, right? I collected X number of samples. You should include your raw data. Typically, I'll ask people to do this as an appendix. Just stick it on the end. I don't need to. I just like to have the raw data because I will go through and verify some of your statistical analysis. I'm not going to verify all of it. That would take forever, but I will spot check it, right? And make sure that it looks pretty good. And then analyze it. Give me some plots. Show me some student t-distribution, and then tell me what you learned. Tell me what you found out. I really want you to treat this like a mini research experiment. If you have any surprising results, tell me about those. Those are the most fun for me, anyway. Right? I don't want to read the same report over and over again. I hope you guys find some cool stuff. I hope you guys think of some cool things to explore. I'm not picky on the length of this report. Honestly, I prefer shorter reports if they're well written, right? If you're concise, if you can give me everything I need to know and you can make it real short, I like that, right? I don't need filler. Don't include filler, guys. Tell me what I need to know. 3 to 5 paragraphs for one question. If you're writing more than 5 paragraphs for one question, you're doing too much, man. Slow it down. That's a lot. And then just email these to me when you get them finished. Just send them to my email address, which is on the homepage of the course website right here. Are there any questions about the setup? I do want to take a look at the code too. Yeah.
If we submit it early, because something additional.
Yeah. Yeah, of course. Yeah, I don't care. Again, you can work in groups of up to 3. I'm very strict about that rule, though. No more than 3 people per group. I'm going to give you some time here at the end of class to form groups and start forming an attack plan for this assignment at the end of the day today. Let's take a quick look at the code, and then we'll call it a day. I did want to show you one other thing before we look at the code about this EQ system. If you ever, like for whatever reason I close this out, whoops, it's actually still there, right? Because I signed it out for 2 hours. So that job is still there. I can still get it back. I go up to job management and it'll show me which jobs I have currently have open. And if I want to get back to it, oh, I have another job open from earlier. Well, this one should be trashed, right? So if I leave one open, I truly want to close it out, I can trash it. I can delete the job. That'll free the resources back up for somebody else to use them, which is a very kind thing to do, right? If I want to reopen the job, I can just open that file again, right? If I remember where I have that file. If you have 100 of them on your laptop like I do, which you probably will by the end of this class, then you can view the actual job and it should allow you to re-download the should allow you to re-download the file, or not, of course. Oh, connect to this session. That's what I want. Here we go. Yeah, so it allows me to re-download the file and log back onto it that way. So let me do this, and then we'll do a quick tour of the code, and then I'll turn you guys loose on it. All right, cool. Here's my terminal. So I'm just going to pull down wget CSE566 1.1.zip. There it is. Zip 1.1.zip. All right, cool. There's not a lot going on here. You got one C file and you got a make file. Let's take a look at the C file first. As promised, it's vector matrix multiplication. Up here at the top, you see the size, n. N is the size, right, of the matrix and the length of the vector. They have to be the same in order for work. They have to be the same. So it's a square matrix and a vector of size 1024. So one of the problems had you change that and examine the aspects, examine how that affects the performance of the code. The random number seed is probably not going to affect anything because we don't care about the actual data here, right? This is purely for performance purposes. It actually repeats it a number of times. This is more to make the program run long enough so that you can actually collect some samples on it. If you don't repeat it, it goes really fast, and then the profilers don't give you a whole lot of information. So this might be worth tweaking as well. Although typically once I find a good value for reps, I won't change it. But I'll leave that up to you. You can do whatever you want. There's only 3 functions, 4 if you count main. It's going to initialize the matrix, which is just going to fill it with a bunch of random value. And then it's going to multiply the vector and matrix together to tell it to using reps, right? And then it will display the output. So here's the random numbers being generated and stuck into the vector and the matrix. Here's the actual matrix multiply routine itself. It's just a nested for loop, as you would expect for vector matrix multiplication. And then here's the output. The output I've allowed you to toggle on and off because actually displaying the output, especially for large matrices, is going to consume a lot of processor cycles. And I don't care how fast the output performance is, right? Vector multiplication is. So at some point, you'll probably want to turn the output off, which you can do by just commenting out this line. Right? That'll turn the output off. In the make file, I give you 3 ways to make it, although now that I thought about this, I might have done this. No, I did this all right. Yeah. 3 ways to make this. 1 if you want to run it with gprof, 1 if you want to run it with operf, and 1 if you want to run it with perf. Right? And I included all the necessary flags so that if you want to use the annotate, you can. Right? So if I decide I want to do gprof, I just say make gprof. It'll compile it with the gprof flags, and now I can run this program with gprof. Or if I want to do the perf version, I can say make perf. It'll compile it with the appropriate perf flags. If you want to use a different profiler, you're more than welcome to do so. You'll have to tweak the make file a little bit probably in order to make that happen. That's okay with me. Like, you can change this code however you want. If you change the actual matrix vector multiply, you better have a damn good reason. You better tell me about that, right? But anything else is really fair game. And so if I run this, then you can see it spends a lot of time just spewing out the results of the vector matrix multiplication. I don't care about the results of the vector matrix multiplication. That's not really the point. And it's gonna skew your results. So like I said, eventually you'll want to go in here and comment out this line so that it doesn't do that. Now it'll just do the vector matrix multiplication without spitting out the results. You see how much faster that went? A lot faster.
Is there a difference, like all these numbers look like they've been generated between 0 and 1 if you use a higher order floating point?
I mean, a float is a float, right? It's going to take up.
Yeah, but does the hardware do the same computation?
Well, in order to generate larger random values, I'd have to multiply and or add or subtract, right? So it's one extra instruction or two extra instructions, maybe, if I have to move it. But
Yeah, but I'm talking on the actual multiplication. Is a float that consists of mostly zeros the same amount of processing as one that has a lot of multiplication?
I wouldn't see what would. We will actually talk about that floating point precision in a lot more detail in the coming weeks. In terms of computation, I can't see that it would have any major effect. But that would be, if that's something you want to investigate, then that could be one of your questions for the homework assignment. Sure. Yep. I know matrix vector multiplication doesn't sound particularly exciting, but in the world of high performance computing, it's a very common operation, right? So it's a good one to use as our entry point into programming this kind of stuff. We're going to see a lot of linear algebra this semester. I hope that's okay with you guys. I love linear algebra too, so it's definitely okay with me. Any questions for me about the homework assignment, about anything we talked about today? Okay, you got like 20 minutes, 25 minutes left. I would highly encourage you to stick around and form up groups and talk about how you want to tackle this. You can use this time to play around with the Linux system and kind of get a feel for it. I also threw up the benchmarks on the calendar that I talked about on Tuesday. So if you want to download the classic benchmarks and run those just for funsies, right? That might be something interesting to do as well. Yeah, question.
The assignment is, you know, you can get groups, so it would be once a month for 3 people.
Yeah, it'd just be one report for however many people. I highly encourage you to at least find one other person to work with, right? The assignments were really designed with 2 people in mind, kind of. Somewhere in that's kind of the sweet spot, I think. So I'd highly encourage you to find at least one other person to work with. But yeah, just one report per group, put all your names on it, and you'll all get the same grade for the assignments. Any other questions? If not, I'll be around to talk to you over the next few minutes and help you out with some of this stuff. Cool.